The problem statement from GATE Physics 2014 reads as follows. In order to measure a maximum of 1 volts with a resolution of 1 millivolts using an n-bit analog to digital converter, working under the principle of ladder network, the minimum value of n is. So in this problem, so what we are given is that we have to use an n-bit A to D converter. So this is a black box, let's say. So this is an A to D converter, analog to digital converter. So on this side, you will have an analog input. It can be anything, right? So voltage, let's say, right? And it will have a digital output, right? So I can denote it something like this. So there are n number of bits. So this is the 0th bit, and there will be the first bit, and then there will be correspondingly there will be the nth bit, and all of these bits have some corresponding 0 and 1. So the maximum range that we can achieve is this will be 0 and this will be 2 raised to the power n minus 1, right? These are, so this will be the decimal value that we can achieve, 2 raised to the power n minus 1 on the output side, by the way. Okay, and so maximum value that so in order to measure a maximum value of maximum of 1 volt, so we are given that the maximum that this can reach is 1 volt. So V max is given as 1 volts, and the resolution of this A to D converter is 1 millivolts. So resolution is 1 millivolts. It's an n-bit converter, and using the principle of ladder network, we'll see in a minute that you see how to implement this ADC. There are different architectures. So there is ladder network, there's a dual slope, there are various other architectures. So what what we'll see is the ladder network, which is a fairly simple to understand, to visualize. So we'll see that in the next slide, and we need to find the value of n. So that's the problem. But first let's have a look at the by the way, this ladder network ADC is also known as flash ADC. So flash ADC implements the ladder network, right? So what we have is, so as we saw that on the output side there will be a Vmin, right? So this will be corresponding to, let's say, 0, and on the out, and correspondingly this is to 2 to the power n minus 1. This is the decimal value, by the way, for the binary number. And correspondingly on the input side, there will be Vmin and Vmax, right? So these are the input side, the analog values, right? And so analog value will be fluctuating, like can be anything, but in between something like this, right? So what's going to happen is that, so let's say at this point of time I need to find what is the digital value, or let's say at this point of time. So how do we find that? What we do is that we create some references. Okay, so we create some references. So this is the minimum. We cannot go below the minimum, you cannot go above the maximum. However, in between you create many reference values. So let's say you have so corresponding to this, let's say we are somewhere here, right? So what will it say is that it will compare the analog value. This is the analog value, V analog. It will compare the analog value to the reference value. So you can see the analog value is greater than Vref2, right? So this will assign it. So this will be corresponding in the value 1, and this will be corresponding 2, right? When you convert it in the decimal, this binary will come out to be 2. Similarly, we can say it's, since it's the cross Vref2, so we assign it the value of 1 0 in binary code. This is the decimal code, and this corresponds to 0 1 0 0 and so on, right? And let's say if it's here just above this, then since it's crossed the yellow line, so it will be corresponding to 3. So this will be 1 1 1. This is the binary 1 1, and there will be preceding zeros. So correspondingly what we need to do is that for every sample of the analog value, we'll compare to this some reference voltages and accordingly assign a digital value to that. But first we need to create all these reference values, and the way to create these reference values is to something called use the ladder network. So on the left of your screen you can see the ladder network, extreme left, this region, right? You can see, so there is some reference which is usually 0 volts, right? So in this case it's 0 volts, and there is a high which is 1 volts. Okay, and in between you will find many reference voltages, 2 raised to the power n minus 1, n minus 2, you can see correspondingly, and green is 2 raised to the power n minus 3, which is here, and Vref1, Vref2, and so on. So this ladder network, just the higher you go in the ladder network, higher voltages, higher reference voltages you will see. And once we have all these reference voltages, now we'll simply use a comparator using an operational amplifier, and we'll compare the input voltage to this comparator. So some of them will go high, and correspondingly will output this this digital output. This is what typically happens in a thermometer. So because you see, when you measure the body temperature or even the atmospheric temperature, so this is the circuitry behind a digital thermometer. So that's what's happening. Yeah. Anyway, so the question talked about resolution, and let's see the resolution quickly. So this is analog to digital conversion, and then correspondingly we have a analog input and digital output. There's a minimum value of an analog value, and there's a maximum value, and so correspondingly there will be a minimum output and maximum output, and we are denoting this on the analog side as V min and V max, and so the difference will be V max minus V min. Correspondingly, the minimum output can be 0 in digital, and the maximum output can be 2 raised to the power n minus 1. This is in binary and encoded as decimal. Right. So note that we are not creating any voltage. We are not providing it. So there is no amplification or attenuation. So the thing on your left should exactly map the thing on the right. So input should exactly map the output. This means V max minus V min should be exactly equal to 2 raised to the power n minus 1. And what is the resolution? Resolution is the minimum value that can be distinctly measured. So what we mean by that, this one bit change. So let's say the value here was something 0 0 1 0. These are the LSBs, and so correspondingly 1 bit change would be 0 0 1 1. Only 1 bit change, right? And this is the resolution. So if you can measure, then that will be the resolution, because output is digital. Okay, so since there are 2 raised to the power n minus steps, which corresponds to V max minus V min, by simply applying the unitary method, you can see one step equal to V max minus V min over 2 raised to the power n minus 1, and we know that this 1 bit change is nothing but the resolution, or the minimum value that can be distinctly measured. So that will be V max minus V min over 2 raised to the power n minus 1. Right. So getting back to our problem, this is the resolution formula that we derived. So resolution is given in the problem is 1 millivolts, right? And V max minus V min. So V max is 1 volt. This is given. The question is silent about V min, but we'll assume it to be 0 because usually it's ground, and even if it's not given, we'll assume it to be 0. So 1 minus 0 over 2 raised to the power n minus 1, right? So I'll take 2 raised to the power n minus 1 to the left side. So this will be 1 over 1 millivolts. So this will give 2 raised to the power n minus 1 should be equal to 1000. This implies 2 raised to the power n should be equal to 1001. Now, there are two ways of doing it. You can take the log and you can just do the calculator, and if you solve this, n will come out to be something 9 point something. Okay, now we cannot have 9 point something, so we can, n is an integer, so n can be 9 or 10 or 11 or 8 maybe. So what the question asks minimum value of n. So if the n were 9, if you take n equal to 9, then you cannot achieve this resolution, because remember that will be 2 raised to the power 9 minus 1, right? So this will come out to be very close to 0.5 millivolts. But if you use n equal to 10, let's try to solve it. So let's try to find this formula. So for n equal to 10, I'll change the pen color so that you can clearly understand. So for n equal to 10, R10 I'm noting it as, so it will be 1 minus 0 over 2 raised to the power 10 minus 1. So this will be 1 over 2 raised to the power 10. 2 raised to the power 10 is approximately 1024, but if I approximate it to 1000, right? So this will come out to be approximately 1 millivolts. So when n equal to 10, the resolution is 1 millivolts, which clearly matches. However, if you were to do, let's say, n equal to 9, which I'm solving it here. So let's try to find out R9. So this will be 1 minus 0 over 2 raised to the power 9 minus 1. This will be 1 over around 511 actually. So if it's around 511, this will approximately come out to be around 2 millivolts. Almost double that. But we need the resolution of 1 millivolts. The lower the resolution, the better. And in order to achieve a resolution of around 1 millivolts, we must use 10. We can use higher also. Let's say if we use 11, so this will again go to 0.5 millivolts. If we use n equal to 12, this will go to 0.25 millivolts. There's scaling of factor of 2. But we need around 1 millivolts, so we'll put n equal to 10, and hence, so our answer here would be the value of n is 10. So that's it. Thank you for listening.